This is an LM317T TO220 case adjustable voltage regulator. You want to put a heat sink on the metal housing. This orange is just going to be my little heat sink, okay? The LM317 generates heat which will destroy it. So the little heat sink on the back of it helps to dissipate the heat off, and it'll last longer. And if you look at the thing, the one side is completely, I screwed that up for you. The one side is completely flat. The other side, you can see the tab, and then you can see the body of the material. So looking at it where you can see the body of the material raised, this is the order of the pins. This one just goes to your battery voltage. The middle one goes to the one input to your switch, because remember the switch, this is always going to be connected to one or the other. So we either connect it back to the ECU where we have true 5-volt reference going through, or we're going to throw the switch and we're going to connect it to our adjusted voltage. So this line will either connect to here or connect to here depending on which way you throw the switch. Our 220 ohm resistor goes between these two legs. And then this is our 1K potentiometer, 1K ohm pot. Now if you take an ohm meter from here to here, no matter which way you turn that, that resistance will never change. The way the pot works is it varies resistance from the central leg to either here or there. And what we're going to do is we're going to adjust the resistance between this and ground. Pardon?
I was writing which wires.
Well, a digital pot's going to have 3 terminals on it. And as long as your middle one goes to ground, you can hook the 317 up to either one of the others. And the difference is that higher voltage, lower voltage if you hook it up one way, and it's lower voltage, higher voltage if you hook it up the other way. So do you want to raise your voltage, lower your voltage? Well, you have to check to see which way it goes, depending on how you have it hooked up. If you do a temporary hook and turning it this way raises the voltage and that lowers the voltage, well, that's backwards of our thinking, so you might want to switch it from this one over to this one and try it again, and it should raise the voltage, lower the voltage as you turn it. So once this circuit is built, you're going to test with your voltmeter between here and ground and adjust it to 5 volts. When you start tuning the car, you want to start tuning the car at 5 volts. So you're going to turn your little screw here on the pot so that you get 5 volts between here and ground. While you're doing the adjusting, take note to how much voltage change you get for, like, say, a quarter of a turn of your pot. If you get a cheapy 3/4 turn pot, I built 4 of these. We had to tune them. Just, went too far. You don't even feel like you moved it, and it just changed half a volt. So if you get a multi-turn pot, then you can actually turn it a little bit and have a reasonable amount of voltage change. And it changes half a volt. Man, that's a bugger to try to tune, especially since we want to be adjusting this at 0.05 volt increments. This is a manual map adjust. So when we discussed the map adjust as far as the 4X optimizer, which would be number 5 on your 4X description, that one will start out at 5 volts when you turn the key on and you start it. And then over the 5.5-minute timeout, it will slowly drop down to whatever you adjust it to. This has no timeout circuit. This goes directly to what you adjust it to. This is a last resort. This means that you've got 208 degrees on the coolant temp circuit. You've turned the oxygen sensor knob so far that you've exceeded its limits and it's not even working anymore. It's just putting out a 0-volt signal. This means that you've put parallel resistance across the air temp sensor and it's reading 230 degrees and you're still not there. Assuming that you have a vehicle that has a MAP sensor, that as we drew it out, you got your ground, you got your VREF, and then you have your signal. And the signal is a DC voltage. EC4 MAP sensors are a frequency, not a DC voltage. Assuming you have this style of a MAP sensor, you can build this simple circuit for $10 or less. You can add it by splicing your like that. Now this will give you more adjustability than you're ever going to need. You can shut the engine down with that thing. You can lean it out to the point where it ain't going to run. You can shut the injectors off with this silly thing. Well, almost. Yes, sir?
What's the dash line between the ECM and the VREF line?
The voltage reference VREF signal, the 5-volt signal going to the MAP sensor, originally went from the vehicle computer into the MAP sensor. Right. So we're going to go in and we're going to cut the wire, and we're going to splice in our switch there, which is connected to our little adjustable voltage regulator. The way this is built, your range will be approximately 1.6 to 6.5 volts. That means you could actually take this stuff and throw it on performance applications, like if you got one of these cars that you put headers and free-flowing exhaust on, cold air induction, maybe a little bit more radical cam, and it just isn't making power for a squat. You build one of these babies, you throw that on the MAP sensor, and you actually increase the voltage going to the MAP sensor. And now with all that, reduced flow restriction, you can richen it back up to where it runs good. Don't ever say I never gave you nothing, guys. And this is on video too, so. But adjustable voltage regulator. Now, this switch is an important component in this system because if you remember yesterday I said when you first turn the key on, most MAP sensors are going to double up and act as a barometric pressure sensor. So when you first turn the key on, the computer is going to take a snapshot of this before you even start cranking. It's going to take a snapshot of this voltage so it knows if we're here in New Jersey or if we're in Denver, Colorado, or somewhere in between. So if you lower the VREF constantly, that barometric pressure signal is going to be reduced also, which is okay. You can tune for that. So you got two options. I've tried both and both seem to work. One is you turn the switch into the normal position, turn the key on, and then as you're cranking, you flip the switch. That works, and you can tune for it. Now you're asking your customer to constantly flip a switch. The other way was to just leave it hooked up like this all the time and then tune for it. But here's the deal. If you're going to build this and you're going to leave the switch so that it's constantly hooked up, you fire up the engine, you got it set for 5 volts. The computer is seeing the appropriate signal for a 5-volt VREF. So its barometric pressure reading is based on actual barometric pressure. Now you go out and you tune and you start adjusting this 5 volts to something less than. And you get it and you're happy and it's good to go. You turn the key off. Next time you start it, it's going to get its barometric pressure reading off of an altered VREF. So what does that mean? It means when you're tuning this manual map adjust, you make a little bit of adjustment, pull off to the side of the road, turn the key off, and then restart it again. Now, whatever tuning you did will be reflected by the new assumed barometric pressure reading. And if you're not quite there, you tune it some more, pull off to the side of the road, shut it off, start it back up, let the computer readjust its barometric pressure reading. Because let's say that you take it from 5 volts and it actually at 4.3, the thing's running great, man. That's right where you want it, 4.3 volts. You turn the key off, you fire it back up. Now the computer sees that you're at about 3,000 feet elevation and all that tuning you did just doesn't work quite as well as it did before you turned the key off. So now you got to, restart it, go back out and make some more adjustments to reflect the adjusted barometric pressure reading. What you want is when you turn the key off, start back up and take it out and run it, that's right where you want it. That was complicated. Did you guys grasp that? Barometric pressure at sea level, 14.7 psi. At the top of Vail Pass, what is it, about 11 psi, 10.5 psi. The higher the pressure, the more air molecules, oxygen molecules, are being pushed into the engine. The engine doesn't suck the air in. We think of it that way because it makes sense to our minds, but in scientific terms, the intake valve opens, the piston drops down, you have less pressure here than you do out here, and the atmosphere actually pushes the air into the engine. So how much push do we have from out here? Well, at sea level, it's 14.7 pounds per square inch of pressure. And at the top of Vail Pass, it's about 10 pounds per square inch of pressure. So how much air, how many oxygen molecules per given volume is the engine ingesting? Well, it has to extrapolate that by creating a barometric pressure reading. What does this map sensor signal mean? It has to be, you have to have a point of reference. So whatever the vacuum, whatever the pressure inside of the engine is, it has to be referenced against how much is pushing in on the engine. So the computer gets that by creating a barometric pressure reading. Incidentally, if you start out at a low altitude and you climb a mountain, climb a mountain, climb a mountain, you get to the top, the engine doesn't quite run to peak. If you pull off and eat at a restaurant or something, fire it back up, and then start driving, it seems to run a bit better. Until you get down to the bottom, then you get down to the bottom, it runs like crap. Pull off and take, a whiz, get rid of that Coke you just drank, fire it back up. Now it runs better again. Why? Because the barometric pressure reading. You turn the key on, the computer takes a snapshot. I don't care how quickly you can go from off to crank. You're not quick enough, the computer's quicker. It will take a snapshot of this signal while you're in the on position, but before you get the crank. It's that quick. I mean, we're talking, a millisecond or two. And so by changing this VREF, you're changing how much pressure the computer sees forcing that air into the engine, which changed the meaning of this value. It means something different if you're at sea level. That same voltage coming off of here has a different meaning at sea level than it does at the top of Vail Pass, and the computer's algorithms know what to do with that. But it has to know where your barometric pressure is. Again, while you're tuning, turn the engine off, start it back up, and see if it's pretty comparable. Do some more adjustments, shut the engine off, start it back up, and verify. Because the barometric pressure reading that the computer takes when you first turn the key on is going to screw up how it reacts to what you did. Trying to throw the whys at you, but as long as you understand what, then we're good to go. If I can better understand the whys, just ask a question so I know how to put it into perspective. This really is a simple circuit to build, though. I'm not an electronics guy, really, I'm not. I had to go look it up, I built 10 of them, and I can't even remember.
Where could you look that up at?
I can tell you how I find it. I know it's on some Jeep site, but I don't remember the URL of the Jeep site. So I go to www.mpgresearch.com, and the category is computer modifications. You click on that. The thread, I think, is called Map Adjuster. It's up to 3 pages as of when I just looked. And then it's like the 4th or 5th entry on that thread. And you click on it and it takes you to some Jeep site. But just now, that's what I had to do to copy the circuit. And it works.
I wrote down higher voltage is richer and lower voltage is leaner on it.
Correct. Yeah, the higher voltage on the adjustable voltage regulator going into your VREF on your map, higher voltage will richen your mixtures, lower voltage will lean out your mixtures. Now remember, the oxygen sensor is going to be king under cruise conditions. This map adjust will do 2 things for you. It will enable you to lean out your transients, so you're wasting less fuel getting on the freeway and that sort of thing. And the other thing it'll do for you is it will lower your lean limits. That will allow you to lean out the oxygen sensor circuit more without the computer giving you a fit. So if you're going to build and install a map adjust, you have to ask yourself, what is your objective? What are you trying to accomplish? Is it to lean out the transients? Is it to lower your lean out limits on the optimizer? Is it both? Do you need it? Is it an extra hassle that you don't need while using an early 3X optimizer? The 4X is going to have it built right in. You may as well use it. Shoot, it's there.
Is that website case-sensitive letters?
No. The website is not case-sensitive letters. Now, you guys are going to get the opportunity to tune. We have a lot of people that we're going to try to shove into 3 vehicles. So you're not all going to get a chance to ride in the vehicle, do the tuning yourself. But I wish we could have each and every one of you tune the vehicle that you worked on. So are there any other questions?